Swayam Prabha. Digital India. Educated India.
So we'll continue the discussion that we had yesterday. Okay. Bhuvaneshwari, your paper is ready from each team. Almost. Okay. Then you can submit that first. Whatever answers you have, you please hand it over from each team. Yeah, Manlal was the team captain, right? Yeah, so from your team, yesterday's that sheet, you can submit that. Your team members are on the way. Okay. Yeah. Thank you. Right. Thank you. Thank you. So your team paper is ready. Thank you. All right. So your team also can collect. Your team also can collect and give to me. Today, what we are doing is, so just take a quick review of what we have yesterday. So each team take a roughly 1 minute, identify something that you learned yesterday. So like bullet points. Okay, make a list of things that you learned yesterday from the class, first class, from my class. Okay, so take a minute, just list it out. One person can list, others can help to give the points. That paper yesterday's.
Yes, sir.
Yeah. Only one. One is. Thank you. That paper. So list out the things that you learned yesterday. Make a list, quick list. Okay, so each team may have some few points, right? We start from this team. 1 point. 1 point that you learned yesterday. One. Fluorescence and phosphorescence. How do you define them?
Same multiplicity in the fluorescence.
Okay. Okay. Another point. Different types of energy. What are the different types? And nuclear. Okay. Another point. Okay. What are those? Okay. both are non-radiative. So classify as IC and ISC as non-radiative process. One is between the states, other one is between the same multiplicity states, other one is between the different multiplicity states. Okay, another one. Okay, how do you define lifetime? Oh, the time scale. Okay, all right. What is the process increasing? Okay, vibrational relaxation, where you place it? First, okay. Okay. And between the states and the internal conversion. Okay. So today what we are going to do is, you learned chemical kinetics. So those principles that we are going to apply to excited states. Some of the things that we learned in chemical kinetics, +2 onwards, those principles we will apply to excited state kinetics. Okay. So for that, there are some terminologies that you must be knowing, but we'll just refresh it. There is something called SSA, steady state approximation. You are familiar about this? Steady state approximation. Okay. So we are going to use this also to find out the kinetics or dynamics of the excited states. Suppose, why do you think this steady state approximation is important? Or let us see, let us take a system and then apply steady state approximation. Then we will see. Just a general system. Say A goes to B, goes to C. Okay. We are going to apply steady state approximation considering B as an intermediate. A go to C is the reaction. This is ground state reaction. Okay. There is no light excitation or anything. Normal reaction. Reactant A is going to product C through an intermediate B. This is the rate constant for this reaction, this is the rate constant for second reaction. Now, when we say I am going to apply steady state approximation, steady state approximation is used whenever the intermediate concentration is steady, called steady state. Okay. So, the rate constant of K1 and K2 will be in such a way that at any point in time where you are observing the reaction, the concentration of B will be a constant. Steady state B concentration. That is the idea of SSA. So, if B concentration is constant, what will be dB by dt? dB by dt means change in concentration with respect to time. So, B concentration is constant. So, what will be dB by dt? 0, because there is no change. The concentration of B is a constant. So, with respect to time, wherever that window that you are observing the reaction, there is no change. So, rate of change will be 0. Right? This is called rate of change of B. So, this is the mathematical representation of SSA. Suppose somebody is asking you what is SSA, you will say that intermediate concentration, derivative of that intermediate concentration is 0 with respect to time. There is no change. Okay. So, now if I say so, then I can also write the right expression of dB by dt. dB by dt means there is a concentration of B which is formed from A, then it is reacting to get the C. So, there is a formation rate and there is a decay rate or a consumption rate. When dB by dt is equal to 0, what does it indicate? Connection between formation and the consumption rates. What will be the relation between formation rate and consumption rate? They will be equal. The panna rate and consume panna rate. They will be equal, then concentration will be the same. So if dB by dt is 0, I can write it as K1 into A is equal to K2 into C. So then C concentration I can write it as K1 by K2 into A. So I will get a expression for the, sorry, K1 into A and K2 into B. B is reacting, no, not C. K1 into A, which is forming B, and B is consumed K2 into B. So these rates will be equal. So the concentration of B will be K1 by K2 into A. That means I can get an intermediate concentration expression from SSI. Now, since concentration of B is constant, the rate of this reaction I can represent as K2 into the like dP by dt, dC by dt. dC by dt means D is the product. I can write either in terms of reactant or in terms of products. So dC by dt will be equal to K2 into B. B is the concentration from which C is formed. So B expression we already have it. If you substitute here, you will get K2 into K1 by K2 into B, which is basically K1 into B. So this will be the rate expression for this reaction if you are applying SSA. Sorry. Yeah, here is A. Okay. I will give you another example. The same way, A goes to B, B comes back to A, B also goes to C. K1, K2, K3. Each team I want you to apply SSA in this case. The same way. These are all ground state, okay? First you individually try, then you can discuss. The only difference is there is a backward reaction from B to A. Here also you are writing dB by dt is equal to 0, which implies that rate of formation of B is equal to rate of consumption of B. First try individually. Okay, now probably just see each other, how the next person is doing, how they are proceeding. You may be halfway through, but let us make sure that everybody is going in the right direction. And if you have confusion, just raise your hand, I will come there. If there are any doubts, you need to ask. What is confusion? Oh, this is your topic. What is an intermediate expression? No, that is not correct. So now, where do you make the mistake? K1A is fine. K2B, K3B. This is also correct. 1 second. Now, this minus sign could be a problem because B is reacting. K3B, B is reacting. Here also B is reacting.
Yes, sir.
So, there is no need for minus sign. Okay.
Okay, sir.
But where do you, so, okay, both are conception of B. So, on one side, this is the formation. Very good. So, now if you remove the sign and then try to see what is that. K1A.
Both is positive.
Okay, 1 second. So, in your intermediate case, show me that expression. This is B. Oh, this is the final answer, right? That's correct. So, first you get the intermediate. Now, you go to the rate of the reaction. What is the intermediate that you got? dB by dt expression. Rate of formation, how many reaction you can identify? How B is formed? A to B. That's the only way. How B are getting consumed? Then another one. So, under term anga vary, inga oru term irikkum. Correct only. Then find out B expression. Expression for B. Root, no, that's complicated. Root will not come. Rate of formation, how do you write rate of formation of B? So, dB by dt, that expression, we need to get rate of formation of B. What will be the expression for that? K1A. No confusion, right? Rate of consumption of B? So, both will be there, no? So, in between plus. K3B plus K1. So, both are a consumption of B. So, it's an additive thing, you need to add it. So, on one side K1A, other side K2B plus K3B. Now, you find out what is B. Got it? Okay. Correct. Now, B concentration is there. Find out the rate for the reaction. How did we do here? Exactly there. B is the intermediate concentration. The next step is using that one, how do you write the rate of the reaction?
Slow reaction under the solid state after equation
So there will be always, when there are multiple steps, one step will be the slow step. You can use in those case steady state approximation rather than the slow step. The idea is that you have an intermediate, its concentration, there are many other rate constants. All these rate constants are playing in such a way that this intermediate concentration remains constant. So obviously one of these rate constant will be slow. So there will be any composite reaction, there will be a rate limiting step that will control the overall rate. So that is one concept which is applicable to everywhere. Okay. Steady state is a special case where there is an intermediate form, and that concentration you can derive using this SSA approximation. It's only an approximation. It's not a exact thing. That means the concentration of the intermediate will change during the reaction. We are assuming dB by dt is 0. That's only an approximation. Okay. So to answer your question, yes, slower step affects the rate of the reaction. That controls the overall reaction. Okay. SSA is on the top of it. It's one more method we can use to understand the kinetics. They are not opposite. I mean, rate determining step is there in SSA approximation. So here, why we are saying the rate is equal to, so in the second case, what will be the rate of the reaction? dC by dt? No. So in the first step, when you write the rate of the reaction, dC by dt is equal to K3 into B. So why we are not considering K1 and K2 is because we assume that concentration of B is always constant. It's a steady state approximation. So it doesn't matter whether K1, K2, there will be always a steady supply of B. So the product formation only depends upon the initial concentration of B. That's why dB by dt is K3 into dB by dt. K3 into B is dC by dt. Okay. So what is the expression that you are getting? Can somebody do on the board? Final expression. Yeah, you got it? What is that? Correct only. Do it on the board. Come. Write big letters, okay? So now whatever you learned how to use SSA, we are now going to do it in the excited stage. These are all just preamble. Okay, just to refresh your memory how to use SSA. Now we are coming to the actual situation where we can apply in the excited stage. You can look at the book also if you want. No problem. Very good. So this is how you use SSA for understanding the chemical kinetics. Correct only, no? Below. Here, right? Yes. So this is also any rate expression will be rate is equal to some rate constant into concentration. That is the rate expression generic thing. So here also you can say rate is equal to some k into A. Only thing is that k is k1 k3 by k2 plus k3, right? This k is actually a combination of the individual steps, rate constants of the individual steps. Okay. So now coming back to our excited state, Jablonski, this is a 3-level Jablonski diagram. Okay. I want you to assign the processes. What is this? Excitation or light absorption. Let us say HNU. What is this? You will be more specific. Fluorescence. So there is a rate for that process. Okay, rate, there is a rate constant for that process. Any process has a rate and a rate constant. So let us call it Kf, right? Rate constant for fluorescence process. What is this? So there is a rate constant for that. KIC. What is this? What will be the rate constant for that? What is this? KP. What is this? Inter-system crossing, right? This is also inter-system crossing. Would that be the same rate or different rate? It will, identical rates for different processes less likely. There will be small differences. So let us represent it as K dash ISC. Okay, so now we have all the rate constant that is needed. Now what I want in teams, what you would work on is these two things. Steady state concentration of the singlet state and steady state concentration of the triplet state. You need to find out the expressions. So I will give you 5 minutes. Think about it, how to go. You can discuss each other. If you have doubts, you call me. I will also come and help you. Yesterday we learned no steady state experiment and time resolved experiment. Steady state means the lamp is always on. So you keep on exciting the molecules. So after some time there will be a steady state concentration for singlet. There is a steady state concentration for triplet. Our concentration expression another, that is what we are trying to get. So Tanya you can do. First you concentrate on S1. Steady state concentration of S1. How to find out? So steady state S1, how do you proceed? Steady state concentration you have to determine for S1. Just a previous example, you see how do you start with the steady state concentration? Same thing. S1 is which one? A, B, C. Hmm? Ah, S1 is when we apply SSA to S1, S1 is B. The intermediate, we are assuming that that is equivalent to that intermediate. Then triplet test, when you apply SSA to triplet, T1 is equivalent to illa beyond. Whenever you are applying SSA, what you are assuming is that is the intermediate. Only intermediates we can do SSA. Intermediate concentration remains constant. That is the idea of SSA. So when S1 you are applying the steady state approximation. In the previous case ABC, which one representing S1 now? Why?
Intermediate.
Whenever you are applying SSA, the idea is that SSA is for intermediates. Intermediate concentration constant, that is the idea of SSA. So if S1 you are saying it is intermediate, then that will be equal to B in the previous case. Okay? So that is one very big question that we need to, at least you identify the question, that itself is a good thing. How to write the rate for that process. Okay, think about it, we'll come to that at least, or LHS you give blank, RHS you write. In a process S1 is formed, and in a process S1 is decay. We have to consider both. And how to write the rate for formation? That's a big question. So you understand that when you say ds1 by dt, S1 is equivalent to B in the previous case. You have to consider S1 as B. That means you are assuming that S1 is an intermediate. And that concentration is remaining constant. That is the idea. So that intermediate is formed, intermediate is decayed. Formation got rate together, decay, there is another rate. And those rates becomes equal. That is SSA. So what is the formation rate of S1? What is the decay rate of S1? Find out. How is it going? S0, yeah. S0 we don't have to consider now. S1 formation, S1 decay. Because S1 is B. In the ABC, we are assuming that S1 as B. That's an intermediate. Intermediate eppadi form pannadhu, intermediate eppadi decay pannadhu. That's all we need to consider. Where how S1 is formed? Only that process, no? Appo oru process then LHS il varum, left hand side. Right side la enna process varum? That's all simple. Now, left hand side, how do you write the right expression is a big, slightly difficult thing. So that we'll discuss, At least right hand side you can write first. Conception. Okay, let me see what is the intermediate concentration of S1. Okay, very good. Very nice. So this is the natural thought process. We'll modify this, but you applied the principle. Okay, that is correct. Everybody is following this, or you can just explain to them. Ensure that in one team everybody is in the same page. Okay. This S1, this is correct. So not K. So T1. Okay, T1 will go. Before that, we need to do something. Concentration time. So there is this is only rate constant, no? So you need to concentration time at this side. Concentration time is there, no? So we need to add the and then get the expression for that intermediate, like B is equal to. You got something like S1 is equal to Like B is equal to there. Where are you getting stuck? What is the doubt? What is the difficulty in proceeding? If you cannot tell that, I cannot help you. Where are you stuck? That you tell me. First equation is formation of S1, rate of formation. How S1 is formed? That process is excitation. So adukku rate expression. That is on the LHS, left hand side. Right hand side line enna varum? S1 to S0 or S1 to T1. So whichever way S1 is decaying, all this we need to consider. So what are the ways S1 is getting consumed? So there is a rate constant, there will be a concentration. Like look at that B case. How do you write it? Exactly like that, no? There are two processes, three processes through which S1 is decaying. And these three processes, there is a rate constant. So there will be a corresponding concentration. So write the expression for the consumption. How did you do exactly in that B case? Got the expression for B? Or sorry, S1? Very nice. So in all these cases, we will modify on the numerator part. Numerator part needs some discussion. Very nice. Here we will discuss. I think some mistake is there. We will come to that. Got it? Very nice. Okay. Where is the expression? If one person gets, I am assuming that everybody in the team reaches that. Okay. How many ways S1 is decayed?
3 ways.
Now the only two terms I am here. Very good. Now S1 is equal to, right? That is the B is equal to kind of thing, expression. Got it? Where is B? Where is S1? Inge. Okay. Can you write it on the board? So in all of the expression that each team arrived has a error in it. We'll correct it now. You're trying for T1? Okay, try it. Oh, you're writing T1 also? Before going to T1, let us stop at S1 because there is some correction on S1. So the same thing correction you can apply for. Good, this is good enough. Okay. So this expression, similar format, all of you who got it. Maybe the numerator term, some you have some rate constant K and R. So the error here is LHS part, which is the formation rate of S1. That is a light induced process, right? A photon is falling, it is getting absorbed, it goes to the excited state. Now, whenever light induced processes are there, generally they are all zero order reaction, which means concentration term will not appear. Zero order means concentration independent, right? Concentration is not affecting the rate of the process. Why it is concentration independent means any light absorption, it all depends upon how much molecules are, how much intensity of the light is absorbed by the molecules. That is the rate limiting step. So if I take 1 millimole, if I take 1 mole, if I take 1 kilogram, but if the amount of light absorbed is the same, varying concentration doesn't affect the rate of the process. Right? So light induced reaction has this catch, bottleneck. It all depends upon how much intensity of the light is absorbed by the molecule that you are taking. So hence this expression that you are going to write here is generally people write is IA, intensity of the light absorbed. That determine the rate of the process. One more assumption is there, every photon that is falling on the system is getting absorbed. That means there is a quantum efficiency of 1. No photons are getting misused or getting lapsed. That is the idea. Okay, so every photon that is falling is absorbed. Then the rate of this excitation depends upon intensity of the light absorbed. This A is very important. Intensity of the light is different, intensity of the light absorbed is different. Okay, so you have to write it as IA. Now S1 is equal to, remaining thing is correct. Your right hand side is correct. So this is the only change that you need to make here. Okay, you make this and then accordingly T1 case I don't think IA is going to come, but let us see what is the T1 expression. All of you got T1? Okay, can you come and write the T1 expression? You can take the book. Come. It's okay. If it is not correct, that's not a problem. Whatever you get. You did not write T1? Don't be afraid to make mistakes. It's not an exam. What is the big deal? You are writing from the beginning, huh? S1 also. S1 Tevela. S1 already we got it. S1 expression we got. I am asking you the other one, T1. You have not done it. Okay. So in the group, anybody has done for T1? Okay. So you can go back and then see. You can work on it. Which group has done for T1? All of you have done. So many of you have done. Okay. So yeah, from your team, come one person. So what is the mistake that in this case, instead of this one, what should you write ideally? For S1, you are writing KHNU into S0, right? That is the rate of formation of S1. So what is the correct expression for that? IA. Okay? Alright. Yeah. Yeah, take it. Yeah, so you can do one more thing. You can substitute the expression for S1 in that. You have an S1 expression there, no? Okay, everybody, is it correct? Any suggestion, correction, modification? Steps are correct? Okay, looks good. So there are initially only two steps through which it is decaying, one step of formation, that is correct. So here light absorption is not coming, that IA is not coming here because this is formed from this stage, right? So that is the formation rate, this is the decay rate. So T1 is equal to this by this. We can put a bracket here mathematically to make it more correct. Then T1 is equal to this S1 expression, you are substituting it. Good. So these are the steady state expressions for singlet and triplet. What is that? Denominator, right? Right. There are four terms coming. So this you bracket it. K, KP, this one. And this is, this is not plus. Oh, okay, there is a mistake. Here it is not K dash. See the correct expression? Kp plus K dash ISC into Kf plus KIC plus KIS. Good point. Everybody got it? Okay. Now, we are continuing, you are using some of these expressions to find out some experimentally verifiable quantities. See, for example, yesterday we talked about lifetime. We said that lifetime, there is not like one time everything is coming down. It's a average time that it spends in the excited state, and that lifetime in excited state chemistry normally represented by a Greek letter called tau. So tau and the rate constants are something like this, inversely proportional, right? 1 by k, or k is equal to 1 by tau. That's a relation. So now, suppose I want you to write the expression for tau f. Tau f is for what? Fluorescence lifetime, right? Now, fluorescence lifetime means lifetime of S1. So, how do you write it? 1 by, so there is can be a confusion here. One is 1 by Kf, that is, but Kf is not the only K that is involved in the process. IA is only absorption. Here, the process in which the fluorescent state is getting decayed, all K's. So, if there are multiple K's there, this expression will be 1 by sigma K. There are many K's are involved. Okay. So, in that case, how do you write TF is equal to 1 by KF plus, right. So, this is the expression for tau F. Now, as you rightly said, there is an expression with 1 by KF alone, that is called tau 0, radiative lifetime. That is it called radiative lifetime. Here the assumption is that S1 is coming to S0 only through fluorescence. Then we say it's a radiative lifetime. That possibility is rare because other processes are also happening simultaneously. But if it is only coming through fluorescence, it is called radiative lifetime. Now let us familiarize with one particular terminology called quantum yield of fluorescence. This is something that you learned in school also, right? Quantum yield. What is the definition that you remember? Quantum yield. Quantum yield essentially means an efficiency. You can talk about quantum yield of anything, right? Quantum yield of fluorescence, quantum yield of phosphorescence, quantum yield of any light induced process. So how do you define quantum yield of fluorescence? What is happening? There is a light absorption process, there is a light emission process, and you need to talk about the efficiency of that process. I have given 10 photons to the system. After excitation, I got 5 photons back. What will be the efficiency? What percentage? 50%. That's the efficiency. How do you get 50%? So how do you define quantum yield of fluorescence now? What is that? So let us say number of photons emitted by number of photons absorbed. So this will be equal, number of photons emitted, I can think in terms of a rate of that process. Rate increase means number also increases. So in terms of the denominator, I can write it as the process rate, which is Kf into S1, right? That is the rate of that process. Rate constant into concentration. This one I can write as IA, right? Photons absorbed, intensity of the light, intensity is number. So in that case, what is IA under steady state condition? Kf plus Kic plus Kiac into S1. So you get a expression for quantum yield of fluorescence as Kf by Kc plus Kic plus Kiasc, right? Now all that I want you to do is, I want you to rearrange this case in terms of lifetime, TOS. I want you to remove all the K from the expression, write the expression in terms of tau. And you know the relation between K and tau. So you write it down, then I will ask one team to tell that. Just write the expression of quantum yield in terms of lifetimes.
SwayamPrabha. Digital India. Educated India.